Assalamualaikum. My name is Aziz Iman bin Muhammad Noor. My MIT ID MBA19605. Today we are from Group 6, want to present heat exchanger. For the introduction, heat exchanger is used to transfer heat from one medium to another without mixing the mediums. A heat exchanger's primary function is to either remove heat from a hot fluid or to add heat to a cold fluid. They are widely used in the space heating, air conditioning, power plants, and so on. There are two types flow arrangement in heat exchangers. For the first one is parallel flow, which is known as co-current flow. Both hot and cold fluids flow in the same direction and enter and exit the heat exchanger at the same end. For the second one is counter flow, which is both the hot and the cold fluids flow in the opposite direction, and both fluid enter and exit the heat exchangers on the opposite end. The objective for this experiment is we want to investigate the effects of the water mass flow rate to the heat exchanger performance, and the second one we want to investigate the performance of parallel and counter flow heat exchanger configuration. For the experimental procedure, there are 9 steps we must to follow. For the first one is the ball valve was adjusted to set the configuration to counter flow or overflow. The second one, we must switch on the centrifugal pump, and the hot water rate V1 was set to 4 liters per minute. The cold water flow rate V2 adjusted to 4 liters per minute. And then wait until the thermal steady state condition is established. Step 5 is temperatures T1 to T4 for both cold and cold water were measured, and step 6, step 3 to step 5 were repeated by varying the cold water flow rate V2 to 6 liters per minute and 8 liters per minute. For the step 7, the experiment was repeated by adjust the hot water rate V1 to 6 liters per minute. And then the experiment was repeated by adjust the hot water rate V1 to 8 liters per minute. For the last step in this experiment, after the experiment, the heater, centrifugal pump, and the cold water supply were switched off. That's all from me. Thank you.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Harib Abdullah. ID number MA19202. Today I will discuss and share about the result for parallel flow experiment data for hot water tank temperature setting at 60 degrees. So this data have been given by our instructor. So we get the hot water flow rate, cool water flow rate, hot water, cool water. Okay, this is calculation result for the parallel flow configuration. So this result I get when I use the equation and formula in the next slide. So I will tell and share about the sample calculation for hot water 4 liter per minute. Okay, for the CP I will use 4.2 kg per kilogram degree Celsius, and raw water density of water 1000 kg m cubic. So the first one, we get the value of mass flow rate, m dot equal to rho multiplied by v dot. So v dot we get by 4 liter per minute multiplied by 1 minute over 60 seconds multiplied by 1 meter cubic divided by 1000 liter. After that, we get the value of QH, and the formula of QH equal to m dot h multiplied by CP multiplied by TH1 minus TH4. TH1 minus TH4 we using at this result. So after that, we get the value of QC. The formula for QC is m dot multiplied by Cp multiplied by Tc4 minus Tc1, and we get the Qm, which is QH plus QC divided by 2. After that, we can determine the temperature driving force by using log mean temperature difference equation, which is TLM equal to this formula. We can see this formula. And lastly, assume the value of area A equal to 0.0375 meter square. So after we assume, we use this formula U equal to QM divided by AM multiplied by TM. So after we use this calculation, we can get this all the calculation. So I will explain about the graph temperature profile for parallel flow configuration. We can see the temperature gradient for parallel flow. For the x-axis, location of thermocouple, and for the y-axis is temperature. The temperature between the two fluid is high at the entrance end, but it get lower at the exit, and those two fluid temp approach each other as seen in the graph. Two fluid enter from the same end and escape from the same end in this type. This graph clearly correlates to the temperature distribution for parallel flow. And for the comparison of rate of heat transfer, we can see this graph. The rate of heat transfer differs significantly between parallel and counter flow layout. Counter flow fluids go in opposite direction along the heat exchanger. Furthermore, the faster rate of heat transfer could be accounted by the greater average global temperature differential over any unit length. However, as the temperature difference drops, the rate of heat exchange reduces as well. For the blue line is for counter flow, and for the orange line is parallel flow. That's all for me. Thank you.
Assalamualaikum and hi. My name is Muhammad Irfan bin Abdul Jalal, metric ID MA19315. Now I will explain to you about the second heat exchanger, which is counter flow. So, this is the result for counter flow experimental data, which is given by our instructor. As you can see in this table, this is the flow rate value. The value is just the same as parallel flow data, and this is the temperature of hot and cold water, but this value is vary from parallel flow data. So moving to the next slide, this is the results for counter flow configuration calculation that we have made by using the formula. And as you can see here, this is the results for mass flow rate, hot and cold water. This is the result for rate of heat transfer for hot water, cold water, and the mean rate of heat transfer. So this is the result for logarithmic mean temperature difference, and this is the results for overall heat transfer coefficient. Moving to the next slide. So this is the sample formula equation for calculation. Basically, this is just the same formula we used to calculate for parallel flow data. So, but only this formula is different from parallel flow data, which is log mean temperature difference. For counter flow, we use T1 equal to T hot in minus T cold out, and T2 equal to T hot out minus T cold in. Okay, moving to the next slide. So for this slide, we discuss about the temperature profile for counter flow configuration. So as you can see in this graph, the temperature gradient of a counter flow configuration is obviously in the opposite direction for hot and cold water. So the temperature difference between the flowing fluid is constant, which helps to reduce the thermal stresses throughout the exchanger. And the output of cold water temperature may be higher than the output of hot water temperature. So moving to the next slide, this is the comparison of heat transfer coefficient. So based on this graph, the total heat transfer coefficient U is used to compare the performance of various types of heat exchanger. So for the experiment, the heat exchanger counter flow and parallel flow. So this blue line indicates the counter flow and this orange line indicates the parallel flow. So as you can see here, the higher the total of heat transfer coefficient, the better the performance. So based on the results of the calculation have shown that the rate of heat transfer for counterflow is obviously higher than the parallel flow. So to conclude, the counterflow configuration is more effective than the parallel flow configuration. I think that's all from me. Thank you.
Alright, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal with my ID is BMM3531. Okay, today I would like to explain about discussion. So the first question is discuss the effect of the flow rate to the performance of the heat exchanger of the parallel and counterflow configuration. So we can see that from the calculation above, the mean temperature difference of the counterflow configuration is less than the mean temperature difference of the parallel flow configuration. This implies that the efficiency of counterflow configuration is higher compared to the parallel flow configuration for the same heat transfer area and same mass flow rate. Okay, for the next question, what is the difference between parallel and counterflow heat exchanger? So, as we all know, the counterflow heat exchanger are the exchanger in which the fluid flow in parallel but opposite direction, while a parallel flow heat exchanger is the type of exchanger in which the fluid flow parallelly in the same direction. Okay, next, the definition of the coefficient of heat transmission. So, in thermodynamics, the coefficient of heat transmission is defined as the amount of heat transfer per unit area per Kelvin. Those area is included in the equation because it indicates the area over which heat is transferred. Each flow area will be different because it presents the contact area for each flow side. Okay, for the question 4, discuss the factor that will be the effect of the coefficient of heat transmission. So, the thermal property of the medium, the hydrodynamic feature of the flow, and the hydrodynamic and thermal body conditions are all the elements that equal the coefficient of heat transmission. This is due to the fact that the greater the heat transfer between the medium fluid and the surface wall, the greater the amount of heat that may be interacted. Alright, for the last question, discuss errors that might equal the experimental data and how to improve the accuracy of the experiment. Okay, first, the error can be occurred when adjusting the flow rate, as we have to wait for the 5 minutes before recording the temperature reading, or the result may be very from the true value. The eye's position is not directly proportional to the reading of the flow rate meter, and this will cause some difference from the actual reading value. So to improve the accuracy of the experiment result, make sure the position of eye is directly proportional to the reading of the flow rate meter. Whenever setting up the flow rate meter, this will make sure that the flow rate will be set up as instructed and the outcome reading will be more accurate. Okay, for our conclusion, the functioning concept of parallel flow and counter flow of heat exchanging mechanism could be explored conclusively. Based on the calculation, the percentage efficiency in the experiment is greater than 100%, but we can still prove that the counter flow is more efficient than the parallel flow because the percentage efficiency of counter flow is greater than the parallel flow. As a result, counter flow is more dominant than parallel flow. Furthermore, we may deduce that the water could affect the effectiveness of the heat exchanger because the water sources may contain impurities such as sand, dust, and so on. This can impact the result and prevent the heat exchanger from working efficiently. So, as our